At Tektronix, we're inspired by our customers, engineers working on technology that drives the world forward. One such engineer is Professor Andrew Ellis, who began his career in 1994 working on TAT-12 for British Telecom Research Laboratories. TAT-12 was the first optical amplifier-based transatlantic system and represented a major shift in optical technology. Professor Ellis now works at the Aston Institute of Photonic Technologies, where he continues to push the boundaries of optical communication technology.
I did my undergraduate degree in physics, with minor in mathematics at the University of Sussex. At the end of that course, I decided to join BT and get involved in communication. The project I was working on there was optical amplification. And the first system that we installed in 1994 was TAT-12. That was the first optically amplified transatlantic link. It gave BT sufficient excess capacity to do some interesting things with, and one of the things that happened was the growth of the internet. So one of the things that can come as a surprise to a member of the public is how much faster communication signals transmit in the core of the network. So what we do is we don't actually connect you directly with your own hardware when you make an internet call. At the beginning of the telephone age, yes, you actually had a wire that only had your signal on. But now we multiplex lots and lots of people's signals together, transmit it over one fiber. That means it's cheaper for us to do that. That cost saving means that in the core of the network, we're something like 1 million times faster than what you would have in your home. It's been really interesting to see that what I was working on as a core network technology is now in people's homes. And that is trickling down all the time. So what we're doing in the core network today will be in the access network tomorrow, and hopefully in people's homes the day after. Communications, electronic photonic communications, has got a history going back over 3,000 years. The first recorded instance that I've been made aware of was a rabbi communicating back to the chief rabbi in Jerusalem that he didn't know when the Sabbath was, because sometimes the beacons that communicated that were obscured, and the rabbi writing back, the chief rabbi writing back saying, well, why don't you look to the south? There's another set of beacons. Since then, we've had a steady succession of technologies. We've gone from beacons to torches to mirrors. We introduced electronic communications in the 19th century, Wheatstone and Cook, Morse. We switched to optical fibre, and we switched wavelengths in the optical fibre. At each of those switches, we started to get towards not being able to do any more. And it is true that we're starting to get to the limits of what one can do in a single optical fibre. So it's time for another revolution, for another change. The demand for capacity keeps increasing and increasing, but going beyond a terabit is getting increasingly difficult to do that in an energy efficient fashion. So what we're trying to do is reduce the energy consumption that you have with your terabit transponders. And a lot of that energy consumption now is in the signal processing. So our research is looking at eliminating the need for that signal processing, so you don't have to do it and therefore you don't spend the energy consumption on it. But you need to be able to perform either the full signal processing to get a reference line to compare your performance against, or the small amounts of signal processing that are left. And the equipment that you see here is the best way that we could find to obtain the information about the signal, to see what signal processing would be necessary in order to recover the signal and transmit the information.
My research topic is doing energy efficient transponder design. So my motivation is just to simplify the DSP is digital signal processing involved in the transponders. So you have to calculate the complexity of conventional DSP and then make a comparison with our new transponder.
This is an optical phase conjugator. It's a device that you can deploy in optical transmission links, long-haul transmission links, and it can compensate nonlinear noise that accumulates along the transmission, which improves the performance, the capacity, and the reach of that system. We've recently demonstrated 72% reach enhancement of 3.6 terabits per second. That goes from 4,400 kilometers to 7,200 kilometers. It's an extension of, imagine an optical link of, let's say, 4,000 kilometers. The 73% expand that length that you can reach to 7,200 kilometers.
I think what Tektronix have been good at and should continue to be good at is frequency. One of the largest things that we can't do anything about with the energy consumption is just V squared over R, the drive voltage. So the smaller the number of resistances that I need to drive, the better, and that means I need the highest possible bandwidth signals, and that just minimizes the energy consumption. So the continuing push that Tektronix have had on increasing bandwidths, I think that's definitely an area that they could continue with, and that will help push products in that direction as well, and reduce the energy consumption of the internet.
Actually, we are interested in high capacity and improving that capacity, so we always aim for high baud rate, high modulation format transmission systems. That's why we've chosen the Tektronix equipment and the oscilloscopes to realize high detection baud rate and more accurate in their DSP and the results that we can get.
So the most exciting thing for me early in my career was actually seeing the results of the research deployed, so actually getting TAT12 going. Now actually I'm most excited when I hear back from somebody who's worked in my team about what they're doing next.